So without them, I cannot do all the work that leads me to this medal. So where do I start? My journey started from about 12 years ago when I was in Nanjing in Southeast University in China. I attended a Rilem PhD courses where I met quite a few senior researchers like Karen, Professor Jason Weiss, Professor Ole Jensen. I still remember that. At that time, I was very obsessed to the crystallization theory from Professor Jed Scherer in Princeton University. I was thinking, wow, we have those beautiful models of cement and concrete. We have also all these fascinating experiment tools. So I feel we have already understand a lot about cement and concrete. And then soon realized I was wrong. I downloaded this list of currently active TCs from Rilem. So when I took a careful look at them, so all these red arrows, they point to questions that are very much related to cement hydration, to durability problems that people have already studied for more than half century. So I thought we have answers to a lot of things, but we really don't. We still don't know enough about cement and concrete. So why is that? I think it's largely because that concrete is a very complicated material. It's not like a metal, ceramics, or even alloy. Concrete has multiple dimensions of complexity. For example, it's spatial-wise, it has this multi-scale problem. We study hydration, dissolution at very small scale, at atom scale, but if you move on to performance of concrete, you oftentimes will need to go to micro scale, even macro scale. In the meantime, concrete is constantly evolving. The dissolution of cement when it's in contact with water, and then the formation of hydration product, and then the physical chemical change during the long-term surface life of concrete. This adds a significant time dimension to the research of cement and concrete. And on top of that, concrete is a very complicated multi-phase composite material. So we have easily more than 5-6 different materials. Some are crystalline, some are amorphous. So this adds a lot of difficulty to study cement and concrete. So over the years, there are many people, many researchers trying to explore new technologies that help us to understand these problems. So what I've been done over the past few years is based very much on a platform called synchrotron. So synchrotron is a facility where high-intensity X-ray is generated, and researchers develop technologies based on this high-intensity, high-flux X-ray, tunable energy X-ray to study the cementitious material. So the basic theory is not very much different from what we're using in the laboratory. For example, the X-ray diffractometer we use in the laboratory, it relies on how the X-ray interact with the lattice structure of a crystal, right? So it's basically the same. In the synchrotron facility, since the X-ray has more tunable features, higher energy, so we're able to look at a lot of other interactions between the X-ray and our material. For example, the absorption of the material, of certain elements in the material on X-ray, the scattering of a nanocrystalline structure to the X-ray, and also we benefit a lot from this very high intensity in the synchrotron, where the flux of the X-ray can be easily 1 billion times larger than the X-ray source we have in a laboratory. So this allows us to really look at processes in a very short time step, and then to collect signal with very high signal-to-noise ratio. So if we look at all this list of conventional laboratory-based technology, we can actually find a counterpart for almost each of them in a synchrotron-based facility. For example, these X-ray, this pointer. For example, this X-ray diffraction, we have also X-ray diffraction in a synchrotron facility, but What's even better is that we can do spatially resolved X-ray diffraction. Means that you are not looking at only a chunk of powder. You are looking at very small area inside your sample. So this provides you this micro-scale resolution. We can also do it in what this says is the high pressure condition, where you can study how the crystal structure change as a function of the applied load or pressure to the sample. It allows you to study the mechanical property of the crystals. We have also tomography. We have also the scanning electron scanning, X-ray microscope technology. We have this X-ray absorption technology, and this is the pair distribution function. So there's a whole list of synchrotron technology that we can benefit from. We can use them to design experiments to study cement and concrete in an in situ way, okay, and also to study materials despite regardless of their crystallinity. And also we are able to achieve a very high spatial resolution oftentimes. So I will give you two examples of what I have done so far. The first example is on CSH. I think it's of interest to almost everyone who studies cement and concrete. CSH is the main binding phase in our ordinary Portland cement. We know very much about its morphology. We know how it grows, how it precipitates on the surface of a cement particle in the beginning of hydration. We also know that with time it will grow. It will grow into each other and to join the cement particles together. We know a lot about the microstructure, but we still don't know enough about the mechanical property of CSH, particularly at a very small scale. So people do nano indentation, okay, and they use a very small indenter to create an indent on the CSH to understand how stiff it is. But if you look at the results, oftentimes you have very scattered results with a ranging stiffness from about 10 gigapascal to 30 gigapascal. This is a very large variation. And what's more, if you compare that to the theoretically calculated results from molecular dynamics simulation, the scattering is even larger. It can go from 30 gigapascal all the way to 70 or 80 gigapascal in terms of the elastic modulus. So a very important reason of this scattering is because when you do nano indentation, you don't really indent just a solid CSH particle. You're indenting a porous CSH matrix, and oftentimes you don't know what is the porosity of the CSH. So you have almost no control of what is you don't know how to interpret these, the responding of this material to the indenting. So what we want to do is, what we did with this synchrotron technology is that we want to use the super high flux X-ray to be diffracted by our CSH, and when the CSH is in a condition that is hydrostatically loaded to a few gigapascal. So what we did is that we use a very small piece of metal, and we drill a hole in the middle of the metal, and then we load some particles, CSH particles inside, and then we seal this chamber, the small chamber, with diamond. The diamond tip is so sharp that with a bit of external loading, we can easily generate a few gigapascal of pressure inside the chamber. Of course, the chamber is filled also with a liquid medium. So the CSH particles, each of them is swimming in this liquid, and under the high hydrostatic pressure, the diffraction pattern of the CSH will start to shift. So I give you this example here. This is a typical diffraction pattern of CSH. There are some diffraction peaks from impurity material that I block out with this blue band, so you can ignore them. All these red dashed line that points to a diffraction peak from a nanocrystalline CSH. And for example, if you look at this peak, it's usually what we call the basal peak of CSH. It indicates the spacing between the layered CSH structure. So with an increasing pressure, you see this peak starts to move to the right-hand side. That indicates that the spacing becomes smaller. It's shrinking because you apply the pressure. And similarly, if you look at other diffraction peaks related to the dimension within the plane structure, they also shifts to the high angle, means that the whole structure is shrinking. So from Rietveld analysis, we can quantify the lattice parameter change of CSH as a function of the applied load. So here are a few results that we have published. For example, if we look at, for CSH, we have the A and B and C, these three lattice, this edge lengths. C is usually the length along perpendicular to the layer, and A and B are within the plane. We find out that for CSH, so here we study CSH with different calcium to silica ratio. We found out that for all CSH at different calcium to silica ratio, its ability to deform or its stiffness within the plane, the AB plane, is very much the same, despite the change in the calcium to silica ratio. As a function of increased pressure, you have a linear decreasing of the A and B, and from that you can calculate the incompressibility along the A direction and B direction of CSH, and it turns out to be very constant. We also have many other work to show that even if you include aluminium into the CSH structure, it doesn't change the incompressibility within the plane of CSH. What's really different among different CSH samples is that its incompressibility perpendicular to the plane is very different. It can range from, let's say, for this CSH, these red triangles are CSH of a relatively large calcium to silica ratio, 1.3, versus these green ones, calcium to silica ratio of 0.8. The incompressibility can be different by 2 to 3 times. And overall, we can calculate the volumetric change as a function of the pressure. From that, we can calculate the volume stiffness, volumetric stiffness, or elastic modulus of the CSH. And we found out that there's a big difference between CSH that has a larger interlayer spacing and CSH that has a smaller interlayer spacing. If we plot our data, so these red blocks, red diamonds, we plot our data together with the modeled work, we see that in general they are matching at the scale of the value, which is about 50 to 70 gigapascal. But then as the calcium to silica ratio increased, we observed an increased stiffness of the CSH, while in many modeling, it shows a decreasing trend of the elastic modulus of the CSH. So we further conducted our own molecular dynamic simulation and compared with the results of other people, and we realized one important issue is that in many modeling, they did not use an interlayer spacing based on experimental value. Instead, they use, let's say, Monte Carlo simulation or molecular dynamic simulation to determine the most ideal interlayer spacing. So this is not, we know that the interlayer spacing of CSH is not constant. It's going to change as you change the relative humidity of the environment. So the conclusion eventually of this work is that the mechanical property of CSH is mostly dominant by the interlayer spacing of the CSH, which can change when you have a different relative humidity. It can also change when you have aluminum incorporation. It can also change when you have different calcium to silica ratio. So all these conditions should be considered when you are doing molecular dynamic simulation, because it will give you different elastic modulus of the CSH. So this, the novelty of this work is that it really provides the very first direct experimental measurements of the anisotropic incompressibility of CSH along all different directions, and how that change when you change the configuration, the crystal structure of the nanocrystalline CSH. This result can be directly used to validate the molecular dynamic simulation, and can be used as an input value for a from bottom up a homogenization scheme. So I'm showing you the second work using this synchrotron technology, which I did when I was a postdoc in Paul Scherrer Institute in Switzerland. I was in a very big project inside Switzerland to study the alkali silica reaction problem, and it was in collaboration with multiple other institutes. My job is to understand what is the atom scale configuration, atom scale structure. I would not easily call it crystal structure, because at that time we don't know yet whether this ASR product, ASR gel, is a gel or a crystalline product. So my job is to understand what is the atom scale configuration of this product and what is its mechanical property or its volumetric property when it's exposed to different relative humidity. So originally, I think in the textbook that I have learned, the ASR, alkali silica reaction product gel, is often described as a amorphous material. But then in the most recent decade, there are more and more evidence to show that it's not a homogeneous gel. If you look into a concrete that suffers from ASR, you oftentimes will see different morphology. Inside the aggregates, the cracks that are filled with ASR product, those ASR product often have a nanoscale needle shape or plate shape morphology, while the ASR gel outside the aggregates often have a featureless morphology. This easily indicates that the ASR gel is heterogeneous. It's not always the same. We have SEM EDX results to show the element composition that is composed of calcium, sodium or potassium, silicon, and water content. And there's a change of the ratio between calcium to silica and also potassium and sodium to silica. And we still don't know whether these what are the atom scale configuration of these two different products, and how do they react? How does the volume change when it's exposed to a water uptake? Because in the textbook, we are always educated that it's because the gel absorbs water and becomes expanded. So we want to find out whether this is true. We never have this evidence directly at very small scale. So I want to introduce to you this another synchrotron technology called X-ray absorption spectra. This is a very powerful technology when you want to study something that you don't really know its crystallinity. For XRD, you need it to be crystalline, but X-ray absorption spectra, it tells you the chemical environment of certain element, despite its whether it's crystalline or not. So here are examples of the 3 different polymorphs of calcium carbonate. Even they have exactly the same chemical composition, but because of the different chemical environment of the calcium, they give you completely different spectra, XAS spectra. Okay, so from that you can use it as kind of a fingerprint to understand what is the chemical environment of that calcium. So we want to apply this same idea to the ASR product. So what we did is that we collect samples, ASR samples from a lot of real concrete that are affected from this ASR problem. They are collected throughout the whole Europe. We also have prepared reference samples that we synthesized in the laboratory that we collected from minerals, calcium, potassium or calcium sodium silicate minerals that we know the crystal structure. And then we want to do this fingerprint comparison. So here's the result of that I plot all the spectra of calcium absorption edge of the ASR samples from several different places in Europe. What we found out is that despite they are from completely different places and the raw material used to make these concrete are very different, the crystalline morphology product inside the aggregates, they show very consistent absorption spectra, which is very different with the absorption spectra of those amorphous-like ASR product. If you look at the main peak positions, the number of peaks, all the features, they are very much different. So from this fingerprint comparison point of view, it indicates that these 2 different type of material, they are just different. So then we compare these with reference samples. Okay, so for example, all these crystalline product, their absorption spectra, we compare with minerals called schlickovite and another mineral called montanite. I probably will not have time to explain to you why these 2 minerals, but they are long-term suspected as the crystalline form of ASR product. Okay, although we're not completely sure. So we compare with the absorption spectra of these crystalline material as well. We also compare the amorphous one with other amorphous material, for example, here CSH. And we find very strong evidence that If you think these are the fingerprints of this material, actually the fingerprint of the calcium inside the ASR, crystalline ASR product, is very similar to the one in the schlickovite. Okay, this mineral, not the one of called montanite. So we also have other experiments, the micro XRD experiments, and overall we conclude that this crystalline ASR product has a layered silicate structure with the calcium in between two layers and the potassium or sodium embedded in the 8-unit silicate ring inside the silicate layer. Okay, so that's what we found about this crystalline structure. And we found evidence that the amorphous ASR product, at least the absorption spectra, resembles very much, almost identical of CSH. And these are for the amorphous ASR product at the long age, not the early age ASR product. So at long term, when the amorphous ASR product absorbs calcium from the surrounding cement paste, it tends to look like CSH. Okay, that's what we found using this method. And furthermore, we want to understand, so this material, this crystalline ASR, well, it has the layer silicate structure. It reminds me immediately of clay minerals, which is also layer silicate. And clay minerals is known to swell when they absorb water. Okay, so we want to see whether this crystalline ASR product will also swell when it absorbs water. And we want to see that directly under a microscope. So what we did is we do a tomography scan of a tiny sample which is extracted using FIP from a real concrete. This sample contains a very thick vein of the ASR product, the silicate ASR products. And we use a technology called micro-CT, but using the XRD data to reconstruct the spatial distribution of this material. And on top of that, we apply a changing relative humidity. So if you can see this tube, the sample is too small to be seen, but on top of the sample there's a tube where we blow nitrogen that contain different relative humidity to the sample. We want to see how the sample looks like when it's exposed to moisture. So the first result we see is that, well, from this micro-CT using XRD data, we directly get the XRD of the sample. So we look at different layers or different slices of the sample, and we find out that it has, for this sample in general, it has two crystal structure. So judging from the basal spacings, so it means that the layer structure, it has two structures. One has a larger basal spacing, the other has a smaller basal spacing. So one at 10.9 angstrom, the other at about 8.9 angstrom. When you expose it to higher relative humidity, so when you change from high relative humidity to low relative humidity, one of the basal spacing doesn't change, but the other one shrinks, it becomes smaller. Okay? So it means that some of the layer crystals, it is like a clay mineral. It can change the basal spacing when it's wet or dry. And then we use this diffraction signal as an intensity, as a contrast to reconstruct the distribution of the ASR product. We can reconstruct that very well because these crystals are very tiny. They fulfill the so-called powder diffraction requirements, so that you can expect a nicely diffraction ring in our detector. If you have only spots, you cannot do that, but now you have this nice diffraction ring. You can use that signal to reconstruct the distribution. So we did something interesting. We look at directly the reconstruct image of the two different phases, right? One will shrink, the other doesn't shrink. I call it basal 1 and basal 2. We compare their contour, their size, their distribution in dry condition, wet condition, and this is the ambient condition, which is the intermediate relative humidity. And we see that for both types, even one of them will shrink in the crystal structure, but the spatial dissolution actually doesn't change. You don't see the whole agglomeration of the particles starts to swell or shrink when you change the relative humidity. So we look at this, we did also other quantification to confirm this observation, and then we went to this SEM image of crystalline ASR products. And it's obvious that the particles are never completely, the plates are never completely filling the space inside a crack. There are always gaps between the plates. So we interpret this as when you have a change in relative humidity that the plates want to shrink or swell, it only changes the gap between different plates. It's not causing the whole agglomerations to expand or to shrink. At least from our reconstructed tomography, we see that the size of these agglomerations remain constant. So that's what we find. And it's again a challenge to the textbook that it's because of the water absorption that leads to the swell and an expansion cracking of the ASR. We are finding something that's contradicting to that. So we went to alternative hypothesis. For example, this cracking may not be due to this crystalline product. It might happen at very early age due to the earlier form of the ASR product, which might have a different response to the moisture change. Or maybe it's rather because of the crystallization pressure, so the growing of the crystal that opens up the crack instead of this swelling of the crystals that cause the splitting opening of the crack. So that are the two examples I want to show you, and this is my second last slide. I want to discuss with you that apart from this effort of synchrotron technology, there are many other new technologies people are exploring to study cement and concrete. Recent years, we talk a lot about this proton NMR, which is a nice technology to study the pore structure and the moisture condition. We also are we're already seeing some TEM tomography work, which allows you to directly look at single nanometer scale porosity. You can directly look at gel porosity using this technology. So all these technologies, do we need them? So how do we benefit them? How do we benefit from them? My personal view is that we definitely need new technologies, but the development or application of new technologies should always be problem-driven. We should always apply the proper technology, proper probe methods to a specific question. It should be a well-designed experiment so that the results can be analyzed unambiguously to solve this problem. And I think that's how we can truly benefit from this technology. So that is all of my presentation. Sorry, probably I'm running a bit over time. But if you have questions, you're very welcome to email me or catch me off stage.